Present, sir.
Vivekanand,
Present, sir.
Yadav,
Yes, sir.
Yuvraj.
Present, sir.
Okay, today absentees are Prem Vinayak, Kesav Prasad, Arunachalam. So there are 3 absentees today. Okay, so welcome back. We are in the first chapter of emission module. So here we are in the last topic. Now we are discussing about the factors that influence pollutant formation. So here we are looking at the engine design and operating variables or factors that influences the primary pollutant formation. Okay, our focus is on the primary pollutants, SCCO, NOx, and particulate, because they create health effects. So we are looking at the various factors that influence this 4 species formation. The factors are different in spark ignited and compression ignited engine. That's why we are discussing it separately for this 2 IC engine category. Okay, the idea behind identifying these factors is to control the pollutants. Okay, so that is the next step. We are going to discuss that in the next chapter. Before that, we are discussing here about the various engine design and operating factors that influences these 4 pollutant formation. So out of these 4, we know in SI engine we have only 3 species. NOx, in NOx only NO is dominant, NO2 is negligible. Then we have SC and CO. We don't have particulate emission in conventional spark ignited engine. In the last class, I started discussion about the factors that influence pollutant formation in spark ignited engine. So here we are looking at engine design and operating variables that affect this 3 pollutant formation. I will continue the discussion now. So these are the engine design parameters. So we have compression ratio, residual gas fraction, SWAL. So when I say design parameters, these parameters needs to be optimized when you design the engine. So this is at the design stage itself. We need to optimize so as to reduce the pollutant level. Once the engine is designed, once the engine is in operation, we cannot vary these parameters. Okay, that's why they are identified as important design variables that affect the 3 primary pollutant formation in spark ignited engine. So as we discussed in the previous class, we have this compression ratio, which is one of the important design variable that needs to be optimized. Okay, we have you know that we have a range of compression ratio. Compression ratio is a volume ratio, in fact, total volume to clearance volume. So we have a range of compression ratio both for SI engine and CI engine. Okay, so in SI engine also you have a range. Generally, it is between 8 to 10 or so. So you have to carefully optimize this compression ratio based on the engine category. Okay, so that we don't have very high pollutant level. When you increase compression ratio, the immediate effect is there will be increase in temperature. Because of higher temperature, we know that NO formation, which is highly sensitive to temperature, is going to increase. So when we analyze this parameter, as I said in the previous class, you need to recollect whatever we have discussed about the formation mechanism of this 3 pollutant. Okay, you need to recollect whatever we have discussed in terms of formation mechanism of this 3 pollutant, because this design variable, we are going to see how it influences the formation mechanism. For example, if you take NO, nitric oxide, it is highly sensitive to temperature changes in the engine cylinder. We have discussed 3 formation routes for NO: thermal NO, prompt NO, and fuel NO. Thermal NO contribute to 90% of total NO formation, and thermal NO is formed in the high temperature bond gases. So higher the temperature, higher will be the NO formation. Likewise, you need to recollect the formation mechanism of other species, pollutant species, so that we can better understand the effect of these variables on these 3 pollutants. So an increase in compression ratio will increase temperature. Because of that, there will be rise in NO levels in the spark ignited engine. Not only that, higher the compression ratio, higher will be the unbound hydrocarbon emission. the mechanism we have already discussed. You need to recollect that the C formation is highly sensitive to boundary layer fluid dynamics in terms of crevice flow, in terms of adsorption, desorption in lube oil, carbon deposits, okay, and flame wall quenching and bulk quenching. So these are the mechanisms we have discussed. You need to recollect that to understand the effect of compression ratio on HC formation. So HC formation, we say that it will increase with increase in compression ratio, because higher the compression, higher will be the expansion ratio. There is something called post-flame oxidation. Post-flame means after the flame is quenched, there is sufficient time available for oxidizing HC, and that is highly dependent on the temperature level. When you have a higher compression ratio, the expansion ratio is also high. Because of that, during the expansion process, the temperature drop is high. Higher temperature drop during expansion doesn't allow post-flame oxidation. This is one of the mechanisms that is causing higher SC. The other important reason, we know that the crevice contribution to HC emission through crevice flow is around 40%. Okay, higher the compression ratio, higher will be the crevice flow. This is again another mechanism that leads to high HC with high compression ratio. Also, the flame wall quenching. That is, a flame will quench at some finite distance from the wall, cylinder wall. And that is what is the quench distance. The quench distance is also a function of surface to volume ratio. When you increase compression ratio, the surface to volume ratio, will be surface to volume ratio will be considerably high. We have less volume, we have more surface available for heat loss. So flame wall quenching will also increase when the compression ratio is increased. So you could see that all these mechanisms are contributing to higher HC level with increase in compression ratio. So this is one of the important variable. Higher the compression ratio, you have a problem of knock limited compression ratio we already discussed. Not only that, here we could see that higher the compression ratio, we have higher levels of pollutants from SI engine. So you need to carefully optimize and keep a check on increase in compression ratio so that the pollutant levels are not increased much. The second variable we discuss is about residual gas fraction. Residual gas is a gas that remains in the engine cylinder at the end of one operating cycle. Typically, it is around 4 to 8%. But you can vary this quantity of gas that remains in the cylinder at the end of one engine operating cycle by varying two parameters, two important design parameters. One is compression ratio, and other one is valve overlap period. So all these are design variables. That's why it is listed out under design parameter. So by varying compression ratio or by varying valve overlap period, you can change the residual gas fraction. You can increase or decrease the residual gas fraction by doing changes in the compression ratio and valve overlap period. For example, if you increase compression ratio, as I said, the expansion is also high. When the expansion ratio is high, the residual gas fraction will come down. At higher compression ratio, you can expect lower residual gas inside the cylinder. Similarly, valve overlap period is a time at which both the valves are remained in the open condition. Since both intake and exhaust valve are in the open condition, you have intake and exhaust process happening simultaneously. When the intake happens, the gas enters into cylinder at some velocity. And this is helpful in clearing the exhaust gas that remains in the cylinder. Because of that, you have this overlap period. It is causing a process called scavenging. We have already discussed about this. The intake mixture will enter at some velocity, and that is helpful in clearing or removing exhaust from the cylinder. This is what is the scavenging process. Okay, so this effectiveness of the scavenging process is dependent on the duration of the valve overlap. When you have a longer valve overlap duration, you can have more effective scavenging process, meaning you can reduce the residual gas fraction. That is how this parameter is affecting residual gas fraction. But now let us look at how it affects the pollutants. So when you increase, say for example, when you increase residual gas fraction, what you are doing is you are retaining more combustion products inside the cylinder. When you retain more combustion products inside the cylinder, there are two important effects we discussed. One is oxygen level in the cylinder will come down. Since the exhaust is remaining in the cylinder, the fresh mixture volume will get reduced. Thereby, the oxygen concentration in the cylinder will get reduced. The second important effect is the temperature in the cylinder is going to come down. Temperature is reduced because of high specific heat components in the residual gas. For example, CO2 or H2O, they are triatomic gases. You know, triatomic gases will have high specific heat. When the specific heat of the component inside the cylinder is high, it won't allow the temperature to rise because this high specific heat component will absorb thermal energy. It won't allow the combustion temperature to rise. So these two are the important effects of residual gas fraction, and through this effect, it is affecting pollutant formation. When you say that you are reducing oxygen and temperature, obviously the NO levels will come down because NO is highly sensitive to temperature. It also depends on the oxygen availability. When temperature is reduced, oxygen is reduced, you can expect that the NO level come down. So one of the important reason behind increasing residual gas fraction is to put a control on the NO level, especially when the engine is producing high NO. You can increase residual gas fraction and reduce the NO formation. But what will be the other effect of this when temperature and oxygen is reduced? What will happen to HC and CO?
It will increase, sir.
It will increase, obviously, because you have lower temperature that reduces oxidation rate. You have less oxygen that also reduces oxygen rate. So you can see that HC and CO both will increase when residual gas fraction is increased. So you see there is a trade-off between these pollutants. When NO is dropped, HC and CO are increasing. So that's why we often use this word optimization. You have to carefully optimize all these variables such a way that all the pollutants are kept under control. They are not increased too much, right? So you have to carefully optimize because of the trade-off that exists between the different pollutant. Meaning when you reduce one pollutant, you see that the other pollutants are increasing. The next one is swirl level in the engine cylinder. So swirl level, you know, we already discussed in the combustion chapter about SI engine combustion. We also discussed about the combustion chambers. Okay, so one of the important variable when we design an IC engine is the combustion chamber shape. So based on the shape of the combustion chamber, we have discussed that the swirl level or turbulence level in the cylinder is going to be different. Swirl here simply refers to organized fluid motion. Of course, turbulent is unorganized fluid motion, right? Nevertheless, this swirl or turbulence, what it is doing, there is an appreciable fluid velocity inside the cylinder. When there is appreciable fluid velocity in the cylinder, you know the rate at which the flame can propagate is going to be enhanced. So what we are doing by increasing swirl, for example, if you design the combustion chamber in such a way that the swirl is increased, basically we are increasing the flame velocity. When you increase flame velocity, what will be its effect on the combustion process? Say you are increasing swirl.
The flame propagation velocity will increase.
So we are increasing flame velocity. When you increase flame velocity, what effect it will have on the combustion process?
The flame propagation speed will increase.
Yeah, that is what is the IVF. IVF means higher speed, flame speed.
It will burn faster actually.
It will burn faster.
Accelerated.
Yes, accelerated combustion. That will result in high burn rate. So you are burning. So flame is igniting the fuel air mixture. We should always remember this. Okay, flame is igniting the mixture. Ignition at any point of time in an SI engine is through flame propagation. When the flame moves at higher velocity, it is going to burn more unburned mixture. Okay, overall combustion event here is a flame propagation based event. That is how SI engine combustion is taking place. So when you increase the swirl by designing combustion chamber, when you enhance the velocity, fluid velocity, flame velocity is increased, that will increase the burn rate. When burn rate is increased, what will happen to temperature at any given point of time?
It will increase, sir.
Higher.
So temperature is going to be high. Higher the swirl, higher the temperature. Now you can relate this with the pollutant. What will happen to the primary pollutants?
NOx will increase.
NO will obviously increase because there is a rise in temperature with higher swirl. NO is higher. When swirl levels are high, you can directly correlate it to high NO because the temperatures are high. What will happen to HCCO?
SC will reduce, sir, because better mixing means combustion will be better.
Yes.
And
SC will reduce because of primarily because of higher temperature. There is an increased oxidation rate.
yes. And CO will also reduce.
CO will also reduce primarily due to temperature effect.
Yes.
So the swirl level is correlated well with the bond rate. The bond rate is correlated well with the temperature rise. Because of the temperature rise, the oxidation rate of Sc and CO is highly sensitive to temperature. Similar to NO formation rate, highly sensitive to temperature. The oxidation rate of Sc and CO is highly sensitive to temperature. Higher the temperature, higher will be the oxidation rate. Okay, so we know that in Sc and CO, there are two mechanisms. One is formation, other one is oxidation. There will be formation of Sc and CO in the cylinder, but whatever form, most of that will get oxidized if we have sufficient temperature available in the cylinder during the combustion event or after the flame is going. This is called post-flame oxidation. So oxidation is one of the important mechanisms that reduces Sc and CO. For that, you need a higher temperature. So what is the takeaway here is when you are increasing swirl, the temperature is high, that is causing high NO, but that is also causing low Sc, low CO. Again, you could see a trade-off here between these three primary pollutants. So that is how these important design variables are affecting primary pollutant formation in spark ignited engine. These variables, compression ratio, residual gas, and swirl level, they are affecting all these three primary pollutant formation. So we need to carefully optimize them.
Sir, can I make a statement like for any design variable or parameters which is reducing CO and SC emission will have a detrimental effect on NOx emission? Is that right, sir? For any
not always right. It is partially right because what is happening when you increase temperature is so NOx is highly sensitive to temperature. Whenever you increase temperature, NO will increase. Okay. But what will also happen because of increase in temperature, the oxidation rate, as I indicated here, the rate is high. So that has a tendency to reduce Sc and CO. But what you are seeing with respect to the first variable, compression ratio, you see here that when you increase compression ratio, temperature is high, NO is high, but Sc is also high. So here there is no trade-off. Both are increasing. Why it is increasing? Although the temperature is high, as I said, there are several mechanisms that is contributing to Sc. The boundary flow, for example, crevice flow is significantly increasing. Crevice is a major dominant source that contribute to Sc emission. Okay, so when you are increasing compression ratio, there is a higher crevice flow. Because of higher crevice flow, there is high Sc. Not only that, higher the compression ratio, the expansion is also high. Expansion ratio is also high. Okay, expansion ratio is the ratio of the pressure at the start of expansion to end of expansion. That is what I mean by expansion ratio. That will also be high. Because compression ratio is defined based on volume. When you define compression ratio based on volume and say that it is high, expansion ratio will also be dependent on the volume change because pressure and volume are interrelated. Higher the compression ratio, higher the expansion ratio. This will result in considerable drop in post-flame oxidation of Sc. So not only crevice flow, post-flame oxidation is reducing with the higher compression ratio. Although during the combustion event, the core combustion event will result in high temperature, high NO, that is not helping much on Sc oxidation because later part of expansion stroke, you will have a drop in temperature with higher compression ratio. Did you get what I'm saying?
Yes, sir. Got it, sir.
Okay.
Thank you so much, sir.
Fine. So next we are looking at operating parameters. So how these parameters are different from what we discussed just now about design parameter is, these design parameters are modified at the time of designing the engine, whereas this operating parameter can be modified at the time of running the engine. So these parameters, you can say that they are dynamic. They are not fixed. They are dynamic. Design parameters are fixed. You cannot change them when you run the engine. Whereas operating parameters, you can vary them when you are running the engine. That's why it's a dynamic way of modifying this variable, and that will have a control over the pollutant. Now we are going to look at how this variable. So I have listed out 5 important variable as operating variable. All this will have an influence on the primary pollutant. That is what we are going to look at now. Let us see how this is affecting the primary pollutant. To start with, we have this equivalence ratio. So when I talk about equivalence ratio effect on the primary pollutant, you have to just recollect this diagram we have already discussed. So this is phi versus this 3 pollutant. This is 1. When I move towards this, I'm moving towards lean. So this is lean mixture. This is rich. I have drawn this plot for the operating phi range of SI engine. So we know that HC will shoot up both in lean as well as in rich. Lean due to misfire, rich region due to insufficient oxygen. So when I talk about CO, there will be continuous drop in CO when you go below equivalence ratio 1, because lean mixture cannot result in CO formation. CO formation is highly sensitive to insufficient oxygen. That is the primary cause. Okay, there is no partial oxidation of carbon, right? When you don't have any combustion at all, you cannot talk about partial oxidation. Okay, so so it is completely missed combustion. Misfire is the process where combustion is completely missed. So you will have that contributing to HC but not to CO. CO will continuously drop when you move towards the lean region. That is a trend we have already discussed. And when you look at NOx, as I said, with slightly lean mixture, you will have a peak value, NO value. Both in rich and lean side, you will have a drop in NO. So this is NO, CO, HC. So all the 3 primary pollutants are highly sensitive to the phi range that you run the SI engine. Depending on whether it is on the lean side or rich side, you will have an appreciable change in the pollutant level. Okay, in the rich side, you will have very high HC, very high CO. In the lean side, you will have high HC if it is too lean. Otherwise, you will have low HC and low CO. Right, in this region, you could see that there is a drop. Right, and NO is also relatively less. Okay, so it is preferable to move towards lean, except too lean. It is preferable to move towards lean to have a control over this primary pollutants from SI engine. But the problem is when you move towards lean region, what problem I will have on the combustion process?
Stability and this is,
the cyclic variability will increase.
What is that?
Cycle to cycle variability will increase, sir.
Cycle to cycle variability will increase. Okay. Anything with respect to flame?
Sir, the startability will be a problem, sir.
What is that?
Startability will be a problem, sir.
Startability. Okay. I said about misfire. Okay, misfire. From misfire itself, you can guess something
Flame
is
stability
happening.
will be low, sir.
It's lean. What is it?
Flame stability will be low.
Exactly, flame stability. So this is what I'm expecting from you. So flame stability will be poor. Flame stability will come down when you start moving towards the lean zone. So this is exactly the reason. So too rich also flame stability will be poor because there is a very high insufficient oxygen, very high, I mean, when you have a very low oxygen or insufficient oxygen, you cannot maintain a stable flame. So you have a narrow operating phi range where the flame stability is better. This is exactly the reason why we run SI engine with a very narrow phi range, unlike CA engine. We have to run SI engine with a very close stoichiometry or a narrow phi range. Only reason is we have better flame stability. Otherwise, so you know, flame stability, the overall combustion event is flame propagation based event. If you cannot maintain a stable flame, there is no effective combustion that will take place in SI engine. So you need to run SI engine in a very close margin of phi, and that too around stoichiometry. Lean or rich, again close to stoichiometry, right? Don't deviate much from stoichiometry. Otherwise, you will have a problem of flame stability. Okay, since you are forced to run SI engine in this narrow around stoichiometric domain, you end up in creating high pollutant level, which is unavoidable. Okay, which is unavoidable. Otherwise, you won't have an effective combustion that will take place in SI engine. This is the reason why we are creating very high HC, CO, and NO in SI engine. So equivalence ratio is one of the important operating variable. Of course, you can change this value of E by changing the proportion of fuel and air. So if you change m dot F and if you change m dot A, so this is a variable. And this variable can be modified when you run the engine. So it's an operating variable, right? How do you vary m dot F and m dot A? M dot F based on injection pulse width, m dot A based on the throttle valve. So you have a valve in the intake system that controls the flow rate. Okay, at different load, in fact, you are changing the flow rate, but we generally keep same proportion of fuel and air. Okay, based on the airflow, you have to adjust the fuel flow in such a way that you have a similar fee close to stoichiometry. So this is a dynamic variable, operating variable, which you can adjust, but we need to keep it close to stoichiometry in order to have a stable flame. Because of this, we end up in creating high level of all the three primary pollutants. Next, we have this spark timing. So when we talk about spark timing, you have two options. We generally say spark timing in terms of whether it is advanced or whether it is retarded. So this is retarded or delayed spark timing. This is advanced spark timing. Okay, so we are talking about when we are discharging electric spark. So either you can advance it or retard it. So in fact, we need to carefully optimize this important variable spark timing because this is going to affect engine performance. This is also going to affect the pollutant levels that are generated in the engine cylinder. Let us consider the case, advanced spark timing case. So what will happen when you discharge electric spark very early? With respect to pollutant formation, say for example NO, let us start with NO. Suppose if you are advancing the spark timing, that is, you are here. What will happen to NO level?
It will increase, sir.
The first thing you have to analyze is when you are advancing, what will happen to the combustion process? This is what you need to analyze. Combustion process, whether it will create a higher pressure or higher temperature is what you need to think. So when you advance a spark timing, we know we have already discussed about how we can control combustion phasing by changing the spark timing, right? Like considering motoring. So if you advance the spark timing, this is say advanced and this is say retarded. Okay, this is advanced timing in terms of crank angle. This is retarded timing in terms of crank angle. So this is theta and this one is the pressure. This is motoring pressure. Now let us consider the first case, advanced case. So you will have a sharp rise in pressure and you will have a, the slope is also somewhat steeper and it will cause a high max pressure closer to top dead center, and then there is a drop in pressure. There will be an appreciable drop in pressure here, but nevertheless you have a high Pmax value. And the Pmax value is also close to top dead center. Let us say this is top dead center, our reference point. Okay, this is what is happening with advanced timing. When you delay, you could see that the slope itself will be different. Slope is somewhat flat if you delay, right? And pressure rise will be slowly, and then you will have something like this. So you could see that there is a drop in Pmax value when you are retarding the timing. Okay, so so this is what we mean by combustion phasing. So you have different combustion phasing based on when you are discharging electric spark. And this difference in combustion phasing is affecting Pmax, meaning it is going to affect the temperature, in cylinder temperature. So when you are advancing the spark timing, okay, when you are here, when you are advancing the spark timing, obviously there is a rise in temperature. Okay. Because of this, what will happen to NO?
It will increase, sir.
NO is increasing. Now let us think about what will happen to HC. HCCO. Let us first talk about HC.
It will decrease, sir. Decrease. Both of them will decrease.
It will decrease. Why it will decrease? Why do you think it will decrease?
Oxidation, sir. As you told that.
But again, see whatever we have discussed for compression ratio, same effect you can think of here. When you are advancing the spark timing, I said there is a high pressurized rate during compression. When there is a high pressurized rate during compression, what will happen to crevice flow?
It will increase.
So this is one of the major contributor, right? So you should always, whenever you analyze SC, think about what will happen to crevice flow, because that is contributing almost 50% of total SC formation. The rise in temperature will help in oxidation, but you need to look at the timing of rise in temperature. Rise in temperature is happening during combustion period, right? Compression period. I said that once the peak pressure is reached, there will be sharp drop in the pressure. Okay, so there is rise in pressure, reaches a maximum value, there is a drop in pressure. So when I talk about post-flame oxidation is happening here during later part of expansion stroke, not here. So during this region, flame anyway is available, okay? But a post-flame oxidation is happening here. There is a high pressure during compression. High pressure during compression is going to increase the crevice flow. So advancing the spark timing is not good from the perspective of NO as well as SC, because it's rising the SC levels due to high crevice flow. Also, post-flame oxidation is going to come down with early combustion. With late combustion, if you look at the late combustion phasing, you are here with retarded timing, you have a appreciable higher pressure, right? At any crank angle, if you compare these two plots, you see that here you have a high pressure, meaning here you have higher pressure, higher temperature. So during later part of expansion stroke with the delayed combustion phasing, you have high pressure, high temperature. This helps in oxidation. Meaning with retarded timing, you are able to control Pmax and control temperature during combustion. That will help in controlling NO. Also, SC and CO levels will come down because post-flame oxidation will be high. So retarding the spark timing is recommended from the pollutant control perspective, okay, because it helps in reducing NO, it helps in reducing SC/CO also because of increased oxidation. Clear? Next, we have this coolant temperature. Coolant temperature is again is an important variable, especially it considerably affects the SC level, SC/CO level. Now let us look at what will happen with change in coolant temperature. So when we talk about coolant temperature, you need to remember that you have a cooling water jacket. Right, in the jacket you are circulating coolant. I'm talking about the temperature of this coolant. Now let us say that you are maintaining a lower coolant temperature. When you maintain a lower coolant temperature, what are all the effects this will create here, especially around the boundary region?
Temperature will be lower, sir.
The evaporation of fuel will be very, very, very low.
So when you have a lower coolant, when you have a coolant circulated at lower temperature, the wall temperature is also low. When wall temperature is low, there are a sequence of reactions, important processes that will take place because of the lower wall temperature. There are several effects here. One of the effect is you can expect a high crevice flow. Because when the temperature here is low, when the temperature is high, all these are metal, right? Any metal will undergo expansion. When the temperatures are high, there will be expansion of the metal. When the temperature is low, what will happen to the metal? Can I say it will contract?
Yes,
again,
sir. Yes,
sir. All this are happening at the micron level, okay? But nevertheless, this micron level change also will have a considerable effect that you need to note down. So when the temperature of the wall reduces, when the boundary temperature reduces, there will be some contraction of the metallic component, including piston. This will increase this radial clearance. So I can say that there will be more crevice flow when the temperature in the boundary is reduced. And next effect will be on the density of the crevice charge. What will happen to density of the crevice charge when the temperature is less?
it will be high.
It will be high.
It will be high. Okay. When I say density is high, how do we define density? Mass per volume. Volume is always constant here. So what is changing because of high density?
The mass will increase, sir.
Mass will increase. So there are two important effects with lower temperature in the boundary. One, contraction, increase in radial clearance. Second one, increase in density of the crevice mixture. When I say increase in density of the crevice mixture, I'm increasing the mass, crevice flow mass. When the crevice flow mass is increased, its contribution to HC emission will increase. because there is more mass charge that goes into the crevice region with lower coolant temperature. And other effect we discuss about adsorption and desorption from lube oil, right? So in the boundary, you will have a lubricating oil. When the temperature drops, what will happen to viscosity of the lubricating oil? Can I say it is higher?
Yes, sir.
Yes, sir.
When viscosity is high, what I mean here is the oil is becoming thick and thick. When I say oil is thick and thick, what will happen to the lube oil thickness? So it is going to, thickness is going to increase. Instead of thin oil, which will happen at high temperature with low viscosity, you will have a thick oil. Okay, with thick oil, because the temperatures are less here, viscosity is high, oil is thick. When oil is thick, you have more oil to take more HC through adsorption process. So adsorption rate, I would say that it is going to increase when the oil thickness is more. This is what is happening with lower temperature. Also, I said that the solubility is a function of temperature of the oil. When oil temperature is less, solubility is high. When oil temperature is more, the solubility drops. Solubility, I mean here, how much of vapor the oil can hold. That is what is solubility. That is a function of temperature of the oil. When oil temperature is less, solubility is more. So now you could see these effects, cumulative effect of all these processes. One is increased crevice flow, increased crevice mass, oil is thick, solubility is high. What will be its overall contribution with lower coolant temperature?
SC will be high.
SC will be high. So this is the effect of circulating coolant at lower temperature. SC is going to be high because of all this mechanism. Partial oxidation is what is causing SC. That may also result in high CO. Okay, so with lower coolant temperature, especially at the time of starting or warm up, you will have a appreciably lower coolant temperature. This is a function of engine operating condition also. It is highly a transient process, you know. Starting and warm up period, until the engine components reach a steady high temperature, that is what is warm up period, it takes some time. It's a highly transient process, as I said. So during this period, you will have appreciably lower coolant temperature. And this will have appreciably higher HC emission. This is one of the reasons why at the time of starting or up to certain period of time, your engine or a vehicle is emitting high levels of HC and CO. Okay, partial oxidation products in the engine tailpipe will be high at the time of starting. One of the important mechanism is coolant temperature. Coolant temperature is less, so which is causing all these problems of high HC emissions. So from the perspective of controlling the emissions, high HC emission at the time of starting or warm up, you can also have a closed loop control system with a thermostat and see that you are keeping coolant at somewhat higher temperature, maybe using a heating element or something, so that you can avoid a very high HC level in your vehicle. Okay. So nevertheless, this is one of the important variable. Lower the coolant temperature, very high HC level. Engine load, you have to change the load. Okay, whether it is from the pollutant perspective or not, you have to operate your engine over wide load and speed. That is how you design the engine. Now here we are looking at what effect this will create on the pollutant. Suppose if you are increasing load, what I mean by increasing load in an SI engine, how do we do that?
Opening throttle more.
Throttle.
So let us say you are in a full load. So meaning you are allowing more flow of quantity, more charge quantity into the engine combustion chamber. So you are burning more mass. Okay, so you are increasing m dot. The mass that goes into the cylinder is higher at higher load. And you know the energy release, okay, heat release is a function of m dot. As simple as that. So higher the mass, higher will be the heat release. When the heat release is high, what will happen to temperature? Temperature is high. So higher the load, the immediate effect is higher the temperature. So obviously NO will increase, SCCO will drop. Remember, you are not doing anything here. Any other dynamics are involved here, only temperature effect. Okay, you can say that higher the load, higher the mass you are burning, higher the heat release, so temperature is high, as simple as that. That is how it is correlated. Load is correlated with higher temperature. Due to high temperature, NOx formation rate, thermal NO formation rate is high, but oxidation of Sc and CO is also high. That results in lower levels of Sc and CO in the tailpipe. This is the effect of engine load on these three primary pollutants. Now let us look at the speed, engine speed. So you also have to run your engine over a wide speed range. Okay. So when the engine speed is increased, what effect it will have on the combustion phenomena, right? That is what is going to affect the pollutant level. So when speed is high, what effect it will create on the combustion phenomena?
It will be faster because turbulence is increased.
Flame velocity is high, right? Flame velocity, it will have a direct impact on the flame velocity, because you will have appreciable fluid motion. When you increase speed, you are actually increasing the piston velocity. So piston will move up and down at a higher velocity. Okay. And since this is high, the flame will also move at higher velocity. Okay. This piston motion, higher piston motion will also translate into higher charge motion inside the cylinder or higher flame motion inside the cylinder. So flame velocity is enhanced. This is one of the immediate effect of increasing the engine speed. When flame velocity is enhanced, obviously the burn rate will be high. This we have already discussed. So you are increasing the burn rate, meaning you are increasing the heat release in the engine cylinder. This will directly have an impact on temperature level. So temperature is going to shoot up, and when the speed is high. There is another effect with the increase in speed. Can you say that is going to affect the temperature? What is the other effect that is going other than the burn rate, high burn rate?
Heat loss, sir. Heat loss.
Heat loss. So what will happen to heat loss?
With the increase in speed, the time level for heat loss will decrease. So heat loss will be lesser actually in that way.
There are two effects from the perspective of heat loss with the higher speed. One of the effect is the temperature gradient is going to be high, because inside the cylinder, I already said the temperatures are high. Coolant, let us say that you have some coolant temperature, right? The delta T is the temperature in the cylinder, difference in the temperature between the cylinder gas and the coolant. That is what is delta T, which is available for heat loss, wall heat loss. That is across the wall, cylinder wall, you have a heat loss from the in-cylinder charge to the coolant. That is what is the heat loss that we are talking here, and this is dependent on the gradient of temperature. This is high, meaning it will have a tendency to drive more heat loss, but the more dominant effect is, as you rightly observe, the time available for heat loss is considerably less. Here I am talking in terms of absolute time, not crank angle. Absolute time available for heat loss is considerably less when the engine runs at a high RPM. So this effect is generally dominant. Because of that, you will have less heat loss from the engine, meaning you are retaining more heat in the engine. So overall effect is there is a high burn rate, high heat release, there is a less heat loss in absolute time. Okay, all this will create a high temperature, and because of high temperature, NO levels are high. And you can say that Sc and CO are less due to same reason, higher temperature. Okay, so temperature levels are high when you run engine at a higher operating speed, and because of the higher operating temperature, NO levels will rise, Sc and CO will come down because of higher rate of oxidation. Clear? So this is how these variables, engine design and operating variables, have an effect or influence on the three primary pollutants. So having understood this, we need to carefully handle or optimize these parameters so that we are not increasing this pollutant level to a very high value. Okay, very high value will make it difficult to control, even with whatever control system you have in terms of additional devices, after treatment devices that we are going to discuss in the next chapter. So we need to carefully handle these variables in such a way that you are not increasing this primary pollutant levels too much. Any questions here? Okay, so I will get started with this topic and continue it in the next class. So next we are going to look at the same design and operating variable. Here we are going to look at this variable for CI engine. The variables may be different or may be same, but the engine, the effect is different, right? Because the mechanisms involved, for example, HC mechanism is different. CO and NOx, kinetically driven, it is going to be same for SC. It is going to be same for SI and CI, but HC mechanisms are different. So we need to discuss it separately. Also, particulate is another important pollutant emitted from CI engine. So here we have 4 primary pollutant: NOx, you have particulate matter. These 2 are called primarily, significantly high level of NOx and PM are emitted from diesel engine. SC and CO are generally less. We already discussed about that. So cause of concern are not SC and CO, rather it is NOx and PM. So any strategy that you adopt, generally it will be focused on controlling NOx and PM. Okay, now here we are not talking about control, rather we are going to look at the variables that are affecting these 4 primary pollutant, out of which SCCO levels are less, NOx and PM levels are high. In NOx, you also have NO2, which can go as high as 30%, as we have already discussed. So we need to keep in mind that we have these pollutants, primary pollutant, that we need to control from diesel engine. With that background information, we are going to look at this design and operating variable to see how they influence these pollutants. So in terms of design variable, you have 4 variables listed out here. One is compression ratio, then the design of combustion chamber, meaning how we are designing the piston crown or cylinder head is what is the combustion chamber design. Dead pockets in the combustion chamber. So here we have already discussed about this dead pocket in SI engine, because this is affecting considerably the SC emission. For example, crevice is one of the major dead pocket. Apart from that, there are other dead pockets like the seat valve, seats intake and exhaust valve seats. Okay, apart from crevice, you have that, and the gasket, the space available between the head and the cylinder head and the piston top, and the piston is the TDC. Okay, so you need to seal it perfectly, and there are some space available, dead pockets available in those region also, in the head gasket region also. What effect this will create is, this is going to trap air. Unlike SI engine, in SI engine you are compressing fuel air mixture. In CI engine, during intake process, you are taking only air into the engine cylinder. So when you compress, you are compressing only air. Fuel is introduced very late. In fact, near the end of compression only, we are injecting fuel. Until that point of time, you have only air in the engine cylinder. So what this dead pockets, unlike SI engine, will do in a CI engine is, it's going to trap the air inside the cylinder. Okay, so we need to carefully design this dead volumes in such a way that you are not trapping much air. What will happen when you trap air in a CI engine?
The turbulence might come down, sir.
It's not about turbulence. Rather, when you reduce the air level in the engine cylinder, when m dot A is reduced, phi local will become high. Did you get what I'm saying? For the same m dot F, let us say this is constant. For the same m dot F, which you are controlling through injected fuel mass, if you reduce the air mass, you can say that the local phi value is going to rise, because you are reducing air mass. This trapped air in the dead pocket is going to affect the local equivalence ratio. Thereby, it is going to affect the pollutant levels. Other one is injector location. So it's again an important parameter. I will talk more about it in the next class. So you can locate injector at different locations in the cylinder head. Based on that, you will have a considerable effect on the pollutant formation in CI engine. So these are the design variable. Operating variables, you have this fuel injection parameter, primarily timing and pressure. What is the timing of the injection, fuel injection, and at what pressure you inject. These 2 are variables. You can dynamically vary this variable, and that will have a control on the pollutant level. Engine load and speed, you don't have any control. You have to run your diesel vehicle similar to SI vehicle also at different load and speed condition. Now here we are looking at how this operating variable affect the pollutant level. Then there is something called exhaust gas recirculation. You are recirculating a fraction of exhaust, which is a combustion product, into the engine cylinder. Right, that is again an operating variable. You can vary the proportion of exhaust gas that you recirculate into engine cylinder, and that is going to affect the primary pollutants from diesel engine. So these are the operating variables. These are the design variables that are going to influence all the 4 primary pollutants. I will continue this in the next class. I will talk about what effect these variables will create on the pollutant levels. I stop here. It's time up. If you have any questions, I can take them.
Sir, I had one question, not from this topic. Sir, generally, means compression ratio, like if it is 1:15 compression ratio, so we should have 15 bar of air pressure in the chamber, right, sir?
15 bar of air pressure in the chamber. What do you mean by that 15 bar of air pressure?
Sir, like if we have a compression ratio of 1:15, then air pressure means because 15 liter of air is compressed to 1 liter, then we should have 15 bar of air pressure in the chamber, right, sir?
So you are saying that if initial pressure is 1, initial pressure is 1 bar for a 15 compression ratio, P2 is 15 bar. This is what you are saying? Compression ratio is 15.
Yes, sir.
No, it is not that way. You are missing something here. Can you tell me what you are missing?
Temperature.
Not temperature. This is defined based on volume. Yes. Okay. And you are directly correlating volume change with pressure change. You are missing something here. There is a PV relation.
Yes.
Right?
Yes, sir.
PV relation. That is something called index of compression. Okay. This is based on the index of compression, this number is going to be amplified. For example, so when I say P2, according to this relation, P2 by P1 is equal to V1 by V2. Okay.
Yes, sir. Yes, sir. So,
so it is going to change because of the index of compression.
Okay. Now it is clear, sir.
Compression ratio is say V1 by V2, total volume by clearance volume. Okay. Before compression and after compression. That is what is state 1 and 2. So based on value of index, this value is going to change. It's not directly 1 bar to 15 bar with a 15 compression ratio because this index is changing the value.
Understood, sir.
So in fact, it is P1 V1N that is equal to P2 V2N. So V1 by V2 by V2N is equal to P2 by P1. Okay. So that is how you get into this. Based on the value of N, your pressure, final pressure is going to be different.
Understood, sir. Thank you so much.
Okay. Anything else?
Sir, sorry, sir. I slightly joined delayed, sir.
Yeah. I already said twice that you have to join in time because schedule is known to you.
Yes, sir.
Okay. So what is happening is it's frequently happening. I will consider for your case because the first time you are requesting, you also wrote an email to me, but my request to all of you is please be available on time. Don't come late and ask for attendance. It's your responsibility to ensure that you are available on time because schedule is well known.
Sure, sir. Okay.
Excuse me, sir. This is Prem here.
Who is that?
Prem here, sir. Prem Vinayak.
Okay.
I had messaged at 6:05 p.m. I'm sorry for the delay for today alone.
No, that's what I'm saying. Same thing, whatever I said to Mr. Arnachalam.
I understood clearly, sir. Yes. Yes, sir.
So it is not, fair to ask for attendance when you come late, right? You have to ensure that you are coming on time. Because
yes,
this
sir,
is
sure.
third day I'm doing, but what I'm seeing is the number is increasing. So as a kind of, you should not take it in the sense that since I'm giving attendance, if you join anytime, it becomes such a way that I'm encouraging this. My intention is definitely not to encourage. My intention is to discourage this. You need to be on time, right? Punctuality is important.
Understood, sir. Very sorry. Yeah.
Fine. So if you don't have any questions, I stop here. I'll join on Monday, 6 o'clock. Thank you.
Thank you so much, sir.
Thank you, sir.
Yeah. Thank you.
Thank you, sir.